Ever wondered why hot things glow? Like, why does a heated poker turn that, like, red, then orange, then white hot?
Yeah, it's kind of mesmerizing.
Totally. But that seemingly simple question, my friend, well, it kicked off a revolution in physics.
No way. Seriously.
Yeah, we're talking about the birth of quantum physics, and get this, we've got front row seats.
How so?
Through Max Planck's 1920 Nobel Prize lecture, we're basically eavesdropping on a scientific revolution in action.
Wow, that's incredible. Is it like super technical though?
Well, that's the cool part.
Okay.
Planck starts off and he's like, science is messy. It's not some like perfectly linear, neat, and tidy process. It's full of detours and dead ends.
Oh, tell me about it.
He basically walks us through his own struggles to like wrap his head around this whole glowy mystery thing.
Okay, I'm hooked.
Yeah.
So what was Planck trying to figure out exactly?
He was obsessed with figuring out how energy is distributed in the light that's given off by hot objects.
I think I'm gonna need a little help here. What does that even mean?
Imagine heating up a piece of metal, right?
Okay, yeah.
It starts to glow red, right?
Right.
But that red light, it's actually a mix of like all these different colors or wavelengths of light.
Oh, interesting.
Planck, he wanted to understand the exact recipe of those wavelengths. So like how much of each color was in that mix.
So it's like he's figuring out the ingredients of sunlight, but for a glowing poker, you said?
Exactly. And the prevailing theory at the time, classical physics, it said energy should flow continuously, kind of like if you picture pouring water from a pitcher.
Okay, I get it.
Based on that idea, physicists had a prediction for this light recipe. The problem. Their prediction was totally off, especially for these longer wavelengths.
So their recipe, it's like it called for way too much red light.
Yes, it's like the physics world is totally confused because the math just doesn't add up.
So what did Planck do?
Planck's like, hold my beer, classical physics, I'm going in. He starts with this theoretical tool. It's called a resonator.
A resonator.
Yeah, for those of us who aren't like physics whizzes, what's a resonator in this context?
Okay, so think of a resonator like this tiny, tiny tuning fork. Okay. And it can, absorb and emit light energy.
Oh, I see.
So Planck, he imagined a whole bunch of these, resonators, each one tuned to a specific wavelength of light.
Okay.
He figured they were, interacting with the glowing objects, sort of like exchanging energy back and forth.
Yeah, okay, that makes sense. But then I feel like this is where things get really interesting. He hits a wall.
A massive one, yeah.
What happened?
Planck, he realized that no matter how he, tweaked his model using classical physics, he just couldn't get the math to match what scientists were actually observing in the lab.
Oh, I hate when that happens. You're trying to solve this puzzle and the pieces, they just won't fit.
That's a great way to put it, yeah. And that's where this whole reluctant revolutionary part comes in.
Okay.
Planck realized he needed a totally radical, totally new idea.
A scientific Hail Mary.
Basically.
Yeah.
He turned to this different branch of physics. It's called thermodynamics. It deals with heat and energy transfer.
Ugh, thermodynamics. I've heard of it, but to be honest, it kind of scares me.
It's a tough one for sure.
And that's where he stumbles upon this whole concept of entropy, right? Honestly, entropy always makes my brain hurt a bit.
Don't worry, it's a brain twister for everyone.
Okay, good. I don't feel so bad then.
So entropy, it's basically, it's a measure of disorder, or randomness in a system.
Okay.
The key here is that another physicist, Boltzmann, had connected entropy to probability.
Probability, like the odds of something happening.
Exactly. He was essentially saying that systems tend towards states with the highest probability, so the most likely arrangement of things.
Okay, I kind of get it. But how does that help Planck with his, glowing poker problem?
Well, this was Planck's aha moment.
Imagine this.
What is? Instead of energy flowing continuously, like that water from the pitcher we talked about, what if it came in tiny, indivisible packets? Like little bundles of energy.
Little bundles of energy. Like what?
He called them quanta.
Quanta.
Yeah, and you know what? You can't have half a quantum.
Oh.
Like Legos.
Yes. Like little energy Legos.
I love that.
And with this radical energy Lego idea, Planck was able to, get this, he derived a formula that perfectly described what scientists were seeing in the lab. It perfectly described the observed energy distribution of his glowing objects.
Wow.
The Lego-like nature of energy. It explained why that classical physics recipe was so wrong.
Wow, that's incredible. It's like suddenly realizing you've been playing checkers your whole life, and someone just introduced you to 3D chess? Talk about a paradigm shift.
And that's exactly what it was. Planck just cracked open the quantum world.
Wow.
But that's just the beginning of the story. Planck's discovery of these energy Legos, like you said, it led him to these two really important numbers. They're called constants, and they kind of govern the quantum world.
Okay, quantum Legos and quantum constants. I'm intrigued. Tell me more about these quantum ingredients. What do they actually do?
So the first one, it's related to temperature.
And it helps us calculate the mass of molecules. And what's amazing is that, get this, experiments later proved Planck's calculations right.
Wow. So it's like he predicted the weight of a snowflake just by studying the frosty air.
That's a great way to put it, yeah.
That must have felt pretty amazing for Planck. But you said there was a second constant that was even more revolutionary.
Absolutely. It's called Planck's constant, or sometimes it's called the elementary quantum of action.
Yeah.
And it's kind of a mind bender.
Yeah.
This constant, it sets a fundamental limit on how finely energy and time can be divided.
So are you saying there's like a smallest possible unit of time, like a moment so tiny you can't break it down any further?
You got it.
Yeah.
And this had huge implications for physics. I mean, classical physics, it was built on this idea that everything was smooth and continuous.
Right.
But Planck's constant, well, it suggests that at the most fundamental level, the universe is granular. It's made up of these tiny indivisible chunks.
It's like discovering that the universe is pixelated. No wonder some people were skeptical at the time. I mean, did anyone even believe Planck?
You know, even Planck himself was cautious about it. He actually called his quantum idea an act of desperation.
He said that.
Yeah. But what's so compelling is that he then points to all these real-world experiments that were already backing up his theory.
Like what? Give me an example.
I remember the photoelectric effect.
Refresh my memory.
So it's like you shine a light on a metal plate, and boom, electrons fly off.
Right.
That's how solar panels work.
That's right.
Problem is, classical physics, it couldn't explain why this happened. It's like the light was magically knocking these electrons loose.
Okay, I see where this is going.
Einstein enters the scene.
Of course, Einstein.
He used Planck's idea of quantized energy to explain the photoelectric effect. Einstein showed that light, well, it isn't just a wave.
Okay.
It also acts like a stream of particles. So these are little bundles of energy, and they're called photons.
Photons, okay.
And when a photon hits the metal, it transfers its energy to an electron, and it gives it enough of a kick to escape.
Ah, I see.
Suddenly, Planck's, really abstract theory was explaining these real-world phenomena.
That's a seriously elegant explanation. But it gets even wilder, right? Doesn't Planck also talk about Niels Bohr and the structure of atoms?
He does. Planck calls Bohr's work the greatest support for his quantum hypothesis. Think back to, high school chemistry class.
Okay.
Remember those line spectra?
Vaguely. They're like those colorful barcodes you get when you burn different elements, right?
Exactly. Each element has its own, unique spectral fingerprint. It's this pattern of bright lines at specific wavelengths.
Okay.
For decades, these spectra were a total mystery to physicists. They knew the lines, they held clues to the structure of atoms,
Right.
but no one could crack the code until Bohr.
And he used quantum theory to decipher the code.
Exactly.
So Bohr basically used quantum theory and created the first accurate model of the atom. That's huge. It's like finally figuring out the blueprint for the building blocks of matter.
I know, it's amazing, but here's the thing.
Right.
As exciting as these breakthroughs were, they also created this huge dilemma for physicists.
How so?
It's like they had all these amazing puzzle pieces, but they
Yeah.
didn't quite fit together with the existing picture of physics.
Because classical physics and quantum physics were clashing?
Exactly. Imagine trying to fit square blocks into round holes.
Yeah, I see what you mean.
Light, for instance, was behaving as both a wave and a particle.
Right.
How could something be two completely different things at once?
Right. Does that make any sense?
And these weren't just theoretical problems either.
Correct.
They had real consequences for understanding how light interacts with how energy behaves at the atomic level, all that stuff.
So what was Planck's take on this whole quantum conundrum? Did he have any answers?
Well, he acknowledged the challenges for sure.
Okay.
He even called the state of physics at the time unsatisfactory.
He said that.
He did. But you know what's remarkable is his optimism.
Okay.
He compares the situation to the time after Römer discovered the speed of light.
It took decades for someone like Maxwell to come along and unify everything with electromagnetism.
Exactly. And Planck believed that just as Maxwell's equations had brought clarity to the nature of light,
Okay.
quantum theory would eventually revolutionize physics. leading to a deeper and more harmonious understanding of the universe.
That's an incredible thought. It's like he's standing on the edge of a new world, knowing that there's so much more to discover.
And he leaves us with this final mind-blowing question,
Okay.
something to ponder. He asks what happens to a single photon, a single packet of light after it's emitted.
Okay.
Does it spread out like a wave or travel as a particle?
It's such a deceptively simple question, but it's like you said, it cuts right to the heart of the mystery of quantum physics. It's a question we're still grappling with even today.
Exactly. Planck's work wasn't just about finding answers. It was about asking the right questions, the ones that would push the boundaries of our understanding and open up these whole new frontiers in science.
So what does this all mean for us, the non-physicists of the world?
That's a great question. And honestly, Planck's insights into the quantum world, they've had this profound impact on our lives.
Like what?
Everything from lasers, transistors, medical imaging, nuclear energy, quantum mechanics underpins countless technologies we rely on every single day.
It's amazing to think that something as abstract as the quantization of energy could lead to such tangible advancements.
Right, and that's the power of fundamental research. Planck's relentless pursuit of this seemingly simple question about glowing objects.
Right.
It led to a revolution in our understanding of the universe, and it paved the way for countless innovations. It's a testament to the power of curiosity, the importance of asking those fundamental questions, and the enduring impact of a single revolutionary idea.
I love that. So from the early days of figuring out why hot things glow to unlocking the secrets of the atom, Max Planck's journey reminds us that the universe is full of surprises, and that sometimes the most profound discoveries come from asking the simplest questions.
Couldn't have said it better myself.